All right, so we're diving into database internals, huh? I know you've been wanting to get a better handle on how databases work, on a deeper level.
Yeah, definitely.
And it seems like this book is right up your alley,
Yeah.
especially with your backend experience, right?
Mm-hmm.
From what I've heard, this book goes way beyond like basic SQL queries and really gets into the nitty-gritty, like how the data is actually structured on disk
Right.
and how it's all distributed across different machines.
Yeah, absolutely. This book is it really gets into those low-level details. It's great for folks who want to understand like the why behind the design choices.
Right, like the engineering trade-offs
Exactly.
involved in building a database, right?
Mm-hmm.
One of the first things that jumped out at me, at least, was how much emphasis the book puts on storage engines.
Yeah.
It's like the book is saying, hey, if you really want to understand databases,
Mm-hmm.
you got to understand how they store and manage data first.
Yeah, that's the foundation, right? Like the storage engine is really the heart of any database. You can think of it almost like a sophisticated filing system,
Right.
but it's designed for massive, massive amounts of data.
Oh, yeah, definitely. So, like, choosing the right storage engine can have a huge impact on performance. Right?
Oh, absolutely.
Just like if you were picking a filing system for, your own needs,
Exactly.
you would want something that's optimized for how you're going to be accessing those files, right?
Right. So the book, it does a great job of classifying databases based on, how they approach this storage problem.
Okay.
And one of the first distinctions it makes is between row-oriented and column-oriented databases.
Oh, okay. I've heard of those terms before.
Yeah. So in a row-oriented database, all the data for a single row is stored together on disk.
Okay.
So it's really efficient if you want to retrieve an entire row of data.
Right.
But if you're doing a lot of analysis across multiple columns, like you might do in data warehousing, then a column-oriented database might be a better fit because it stores data from the same column
Together,
right?
Right.
So it makes those column-based analyses much faster.
So choosing the right storage engine really depends on what kinds of queries are going to be running the most.
Yeah, exactly. And in fact, it's not uncommon for people to use both,
Oh, really?
for different use cases.
Okay, interesting. So is that like another key distinction the book makes? Like between different use cases and how they might lead to different storage engines?
Yeah, so another big one is disk-based versus in-memory databases.
Ah, okay. So that's about where the data actually lives, right?
Exactly. So disk-based, those are kind of like your workhorses.
Right. The
That-
disk cell.
They offer persistent storage, but of course, disks are mechanical.
Right.
So there are some performance limitations there. But then you have in-memory databases where all the data is kept in RAM, so access is super fast.
But that sounds less durable, right?
Yeah, that's the trade-off. So if the power goes out, you could lose data.
Right. Okay.
So in-memory databases are great when speed is paramount, but you need mechanisms like battery backups or replication.
To make sure that data sticks around.
Right, to ensure persistence. But what's interesting is that in-memory databases, they can often use more complex data structures because they don't have to worry as much about the overhead of accessing data on disk.
Okay, so you've got all this data, right?
Mm-hmm.
Whether it's in memory or on disk.
Uh-huh.
How do databases actually organize it? Like at a fundamental level?
Yeah, so the book talks about pages and blocks as the basic units of storage.
Okay. I've heard those terms, but what are they exactly?
So think of them as like the containers for your data on disk.
Gotcha.
And their size is often determined by the physical limitations of the storage medium,
Okay.
specifically the size of disk sectors. So it's interesting how even at this low level, the physical world kind of constrains the digital world.
Yeah, it's like we can't escape the laws of physics, even in the virtual realm, huh? But with these fixed size pages, how do databases manage to efficiently store and retrieve data, especially when you've got data of all different sizes?
Yeah, that's where things get really clever. So most disk-based databases rely on this powerful data structure called a B tree.
Ah, B trees.
Yeah, have you heard of them?
I have.
Okay, so B trees are designed to minimize the number of disk seeks required to find a specific piece of data.
Right, because disk seeks are slow, right?
Very slow. So they do this by having a high fan out.
What does that mean?
So that means each node in the tree can have many children,
Okay.
which keeps the tree relatively short so you don't have to traverse through as many levels to find what you're looking for.
Okay, so it's not just about storing the data.
Right.
It's about storing it in a way that makes retrieval efficient.
Exactly. And to make things even more efficient, there's this clever technique called slotted pages.
Slotted pages?
Yeah, so instead of having like these rigid fixed size slots for data,
they use a more dynamic approach.
Okay.
It's kind of like, imagine you have a toolbox, right?
Yeah.
And you can rearrange the tools as needed.
Right.
That's essentially what slotted pages allow you to do with data.
Okay.
This flexibility is really important when you're dealing with data of varying sizes, like strings.
Right, because you don't want to waste space.
Exactly.
If you have a short string, it shouldn't take up the same space as a really long string, right?
Right. And for those really long strings or other variable-sized data, databases will often use a technique where the actual data is stored separately.
Okay.
And then you use pointers within the pages to reference it.
Okay. So it's like having a separate warehouse for oversized items.
Exactly.
And you just keep a reference to their location in your main inventory.
Exactly. It's all about optimization. But speaking of making sure things are stored correctly, how do we actually ensure that the data hasn't been corrupted during storage or retrieval?
Right, because disks aren't perfect. No, they're not. So that's where checksums come in.
Oh, right. Checksums.
Yeah, they're like digital fingerprints for your data. So when data is written to disk, a checksum is calculated based on the data's content.
Okay.
And then this checksum is stored along with the data. When you read the data back, the checksum is recalculated.
Right.
And if the calculated checksum matches the stored checksum, then we can be confident that the data hasn't been altered.
So it's like a built-in safety check.
Exactly, a built-in safety check. And the book goes on to explore even more advanced concepts like lazy B trees.
Lazy B trees, what are those?
So these try to minimize write operations for efficiency. So instead of writing every change to disk immediately, they kind of batch up changes and apply them in a more optimized way.
So it's like delaying gratification.
Yeah, exactly. Delaying gratification for efficiency.
For efficiency's sake. Interesting. What other interesting storage engine concepts are there?
Well, the book dives into something called log-structured merge trees, or LSM trees.
LSM trees, okay. Are those completely different from B trees?
They're related, but we can explore that further in a bit. But first, I think it's time to shift our focus to the second major aspect of the book, which is data distribution.
Okay, yeah, because we've talked about how data is stored on a single machine, but how do you scale that up to multiple machines?
Right, and that brings a whole new set of challenges. The book calls them the fallacies of distributed computing.
Fallacies of distributed computing. Okay, I'm intrigued. Tell me more.
Well, these are common assumptions that developers often make about distributed systems. Assumptions that, unfortunately, turn out to be false in the real world. For example, we can't assume that networks are perfectly reliable.
Right.
Or that communication is instant.
Yeah, makes sense.
Or that a single node failure won't disrupt the entire system. So we have to design our systems with these fallacies in mind.
Okay, so it's like a whole new set of rules and challenges.
Exactly.
I'm definitely curious to learn more about how databases tackle these distributed computing challenges.
All right, well, let's dive in, starting with a deeper look at how log-structured storage plays a key role in modern database design.
Okay, so we're about to jump into this world of data distribution.
Right.
But you mentioned log-structured storage and how it plays like a big role in modern database design.
It really has.
Even in like distributed settings. What's so special about that approach?
So log-structured storage, it's really kind of revolutionized how we think about managing data.
Okay.
And it's used in everything from flash drives to file systems to, of course, databases. And the core idea is to optimize write operations by appending new data to this log-like structure.
Okay.
So imagine like a journal where you only add new entries.
Okay.
You never go back and like erase or modify old ones.
Right.
You just keep appending.
Gotcha.
And this turns out to be remarkably efficient, especially when you're dealing with lots of small random writes.
Yeah, that makes sense.
Because instead of constantly seeking and updating data in place, you're just adding to the end of the logs.
You're not jumping around all over the thing.
Exactly. And by grouping writes together, you minimize those expensive disk seeks.
Right.
And achieve much higher write throughput.
Okay, so that's the benefit.
Yeah, but of course there's a trade-off, right?
There's always a trade-off.
Always a trade-off. Yeah. So to reclaim space, that's occupied by deleted or outdated data.
Yeah, you got to clean up.
You need to perform garbage collection periodically.
Okay.
And this involves identifying and consolidating the active data.
Right.
which is a bit more involved than just, deleting a file.
So it's like cleaning up your attic every once in a while.
It's a great analogy.
You have to sort through everything
Yeah.
and decide what to keep, what to toss, what to reorganize.
Exactly. And this brings us to this fascinating family of database systems that heavily leverage these log-structured principles called LSM trees, or log-structured merge trees.
LSM trees. Okay, I've heard of those, but I don't know much about them.
Yeah, and they're becoming increasingly popular, especially in systems that handle these massive write workloads.
Okay, so what makes them so good at that?
So LSM trees, they combine the write efficiency of log-structured storage with the read efficiency of sorted data.
Okay, so they combine the best of both worlds.
Yeah, they do this by using this clever combination of in-memory and on-disk structures.
Okay, I'm listening. Break it down for me.
All right, so LSM trees typically have two main components.
Okay.
You have this smaller in-memory component called a memtable,
Memtable?
which acts as a buffer for incoming writes.
Asha.
And then you have a larger disk-resident component that consists of multiple sorted files called SSTables, or sorted string tables.
SSTables. Okay, so new data first goes to the memtable,
Right.
which is like a temporary holding area.
Uh-huh.
And then when it reaches a certain size,
Yeah.
it gets flushed to these SSTables on disk.
Exactly. And to maintain order and efficiency, LSM trees employ this process called compaction.
Compaction, what is that?
So compaction involves merging multiple SSTables into a single larger SSTable
Okay.
and discarding any deleted or outdated data along the way.
So you're cleaning up as you go.
It's like combining, several smaller notebooks into one larger notebook.
Right. Makes sense.
Eliminating redundant or obsolete notes in the process.
I like that analogy.
So this compaction process is crucial for keeping things organized and efficient.
Okay. But when you need to read data from an LSM tree, how do you know which SSTable to look in?
That's a great question.
Because there could be many of them.
Right, so that's where indexing comes into play.
Ah, indexing.
Yeah, so LSM trees use various indexing structures, like B trees or skip lists, to efficiently locate data across those multiple SSTables.
Gotcha.
And these indexes are often kept in memory for fast access.
Okay, so it's like having a table of contents for a large library.
That's a great analogy.
So you know where to go.
Exactly. They guide you to the right section for the information you need.
Okay, so it's not just about storing the data efficiently.
Right.
It's also about being able to find what you need quickly.
Exactly. And to further enhance read performance, LSM trees often employ techniques like Bloom filters.
Filters? What are those?
They're these probabilistic data structures that can quickly tell you whether a specific key might exist in a given SSTable.
Okay.
So this helps avoid unnecessary disk accesses, especially when you're searching for keys that don't actually exist.
So it's like a quick check at the library entrance
Yeah.
to see if the book you're looking for even exists before you go searching the shelves.
Exactly. They act as a first line of defense against unnecessary searches.
I like it.
Makes the whole process more efficient.
Okay, so are all LSM trees implemented the same way?
There are some variations. Some are leveled, meaning they organize SSTables into different levels based on their size.
Okay.
And this helps to balance write and read performance by minimizing the number of SSTables that need to be merged during compaction.
So it's like having different tiers of storage.
Yeah, exactly.
Within the database itself,
Right.
where you keep more frequently accessed data in faster, smaller SSTables.
Right.
And then less frequently accessed data can go in those larger, slower ones.
Exactly. It's a tiered storage system within the database itself.
To optimize for both speed and efficiency.
Precisely. And these optimizations are essential because one thing we have to be mindful of with all these clever story systems is something called write amplification.
Write amplification. What's that?
So write amplification refers to this phenomenon where writing a small amount of data to the database can actually result in a much larger amount of data being written to the underlying storage medium.
Okay, why would that happen?
It often has to do with the underlying storage technology itself.
Okay.
For example, flash memory, which is used in SSDs,
Right.
requires data to be written in blocks, even if you're only modifying a small portion of the data.
Okay.
So this means that even a small write can trigger an entire block to be rewritten,
Got it.
leading to write amplification.
So it's like repainting an entire wall.
Exactly.
Just to change the color of a tiny speck.
Perfect analogy.
Yeah.
So even though we're making these incredibly efficient systems on the database level,
Right.
we still have to be mindful of the limitations and the quirks of the underlying hardware.
The laws of physics still apply.
Exactly, and that's why techniques like log-structured storage, which groups writes together,
Right.
and algorithms like copy on write, which avoids modifying data in place, are so important in modern databases.
So it's all about minimizing those unnecessary writes.
Exactly. They help mitigate the effects of write amplification and ensure that our storage systems remain performant and efficient.
This has been super helpful. It's amazing to see how these systems balance like performance, reliability, and efficiency.
It's quite impressive.
To manage all this data we generate.
Absolutely. It's a testament to the ingenuity of the folks who design and build these systems.
Yeah, for sure. Okay, so now that we have this understanding of these storage fundamentals, are we ready to tackle the complexities of data distribution?
Yeah, I think we are. So let's explore how databases scale to handle those massive workloads across multiple machines.
Okay.
And I think the fallacies of distributed computing that we touched on earlier are a great place to start.
Right, because we need to understand the challenges before we can appreciate the solutions. Okay, let's break down those distributed system barriers and see what's on the other side.
All right, let's do it.
Okay, so we've explored storage engines pretty in depth.
Like how?
And even touched on those tricky write amplifications. But now it's time for the main event.
Yeah.
Distributed databases.
All right, let's get into it.
You mentioned those fallacies of distributed computing.
Yeah, those are important.
What are they exactly? And how do they mess with database design?
So the fallacies, they're these assumptions that developers often make about distributed systems, assumptions that just don't hold up in the real world.
Yeah.
For example, you can't assume networks are perfectly reliable.
Right, they're not.
Or that communication is instant.
Yeah, there's always some latency.
Always. Or that a single node failure won't, totally disrupt the whole system.
Okay, so these are the assumptions we need to ditch when we're building distributed databases.
You got it.
Can you give me, a real-world example of how one of these fallacies could cause trouble?
Sure. Let's take the fallacy of reliable networks.
Okay.
Say you have a database spread across several machines, and you start a transaction that updates data on, a bunch of these machines.
Right.
Now, if the connection between two of those machines drops right in the middle of the transaction, you could end up with inconsistent data.
Oh, I see.
Some machines got the update, others didn't.
Yeah, that's a problem.
Big problem.
So if we can't rely on the network, how do we make sure that data updates happen consistently on every replica?
Well, that's where things like consensus algorithms come into play.
Consensus algorithms?
Yeah, these algorithms, they make sure that all the nodes in the system agree on the same values or actions, even when there are failures.
So it's like a group vote?
Yeah.
And the majority wins.
Exactly. Everyone agrees to stick with the outcome.
Even if some folks are missing or disagree?
Right. So you have a single source of truth for the data.
I like it.
Even with an unreliable network.
What other tricks do databases use to deal with these distributed computing headaches?
Well, one of the first things you need is a way to detect failures.
Right. Got to know if there's a problem.
Exactly. And you can't fix what you don't know is broken.
So how do they do that?
Databases use all sorts of mechanisms like heartbeats.
Heartbeats?
Yeah, those are like periodic messages that nodes send to each other just to say, hey, I'm still alive.
Gotcha.
And if a node goes silent, others assume it's failed.
Like checking in with your buddies.
Exactly.
Be sure they're still around.
What else? Oh, gossip protocols.
Gossip protocols. What are those?
Those are like a network of friends sharing info about who they've seen recently.
Okay, so heartbeats are checking in. And gossip protocols are like sharing the latest news.
Exactly.
Okay, so you detect a failure, then what?
Well, then the system has to adapt and keep going. This often involves replication.
Replication, right.
Where data is copied to multiple nodes.
For backup.
Yeah, to ensure availability.
Okay.
And then there are failover mechanisms.
Okay.
Where a standby node takes over for a failed node.
So it's like having an understudy ready to go.
Precisely.
So distributed databases have a lot of built-in redundancy.
Yeah, a lot.
To deal with failures.
That's all about resilience.
Makes sense.
Yeah.
But what about the data itself? How do we make sure updates are transmitted correctly between replicas? Especially with those pesky network delays, duplicates, even lost messages.
Right. Well, that's where reliable messaging comes in.
Reliable messaging.
Databases use a bunch of techniques to guarantee message delivery, even with network hiccups.
Okay. Like what?
Well, one is acknowledgements. The receiver sends a confirmation back to the sender.
Like a return receipt.
Exactly. So the sender knows the message arrived safely.
Makes sense. What if the sender doesn't get an acknowledgement?
Then it assumes the message was lost and sends it again.
Oh, okay.
Another important technique is message ordering,
Okay.
which makes sure messages are processed in the right order.
Right, because things could get jumbled up with network delays.
Exactly. Imagine a system where transferring funds from one account to another involves multiple steps.
Okay.
Message ordering ensures these steps happen in the right sequence.
Even with network delay.
Even with delays.
That's crucial.
Absolutely. But what about duplicate messages?
Oh, yeah. If you're resending messages, you could end up with duplicates.
Right, and that's where idempotency comes in.
Idempotency. That's a mouthful.
It is, but it's a powerful concept. It means an operation can be executed multiple times without changing the outcome.
Okay.
Like pressing the elevator button a bunch of times.
Right. It will make it come faster.
Exactly. So even if a message gets delivered and processed multiple times, it won't corrupt the data.
So it's a safety net against those duplicate messages.
Precisely.
It seems like there's a lot of effort to keep distributed data consistent
A lot of effort.
while still making sure everything's fast and always available.
It's a delicate balancing act.
Right. That brings us back to the TAP theorem. You can't have perfect consistency, availability, and partition tolerance all at the same time.
That's the trade-off.
So how do distributed databases manage to juggle all these demands?
Well, different databases make different choices based on what they're designed for and the kind of workload they handle.
Makes sense.
Some systems go for strong consistency,
Okay.
even if it means being unavailable during network partitions.
Gotcha.
Others might choose high availability, even if it means living with temporary inconsistencies.
So there's no one right answer?
Nope. Depends on what you need. Can you give me some examples of how databases prioritize those CAP theorem elements? Sure. Think about a financial app that needs strict transactions.
Okay, like a bank.
Exactly. They might choose consistency over availability.
So it's better to be temporarily offline
Right.
than to have incorrect transactions.
Exactly. On the other hand, a social media app
Okay.
might prioritize availability over strict consistency.
Because people need their social media fix.
Well, yeah, but also because it's okay if some users see slightly outdated data for a short time.
Okay, I see.
The important thing is keeping the system up and running.
So the way you balance these CIP theorem elements is a big decision.
It's huge.
It really shapes the whole database.
Absolutely. And to manage these trade-offs, distributed databases use different consistency models.
Right, we talked about those.
Each with different guarantees and trade-offs.
Like linearizability.
Yes.
The strongest guarantee.
But often at the expense of performance.
Right. And sequential consistency, which allows for some reordering of operations,
Okay.
but still guarantees consistency within a single process. Those are the stricter models,
Yes, but they're also weaker models.
like eventual consistency.
Right. Often used in systems that need high availability.
Can you remind me how that works?
Sure. With eventual consistency,
Yeah.
the system promises that all replicas will eventually be the same,
Okay.
but allows for temporary inconsistencies.
So it's like eventually everyone gets the same news.
Yeah, exactly.
But it might take a bit longer for some folks.
Precisely.
Are there specific techniques databases use to implement these different models?
Absolutely. We talked about quorums, which need a certain number of nodes to agree before something's considered successful.
Right, for stronger consistency.
Yeah, for weaker models like eventual consistency, databases often use anti-entropy mechanism.
Anti-entropy mechanism.
Yeah, those are like background processes that constantly work to find and fix inconsistencies between replicas.
Like data detectives.
Exactly. Always on the lookout.
What are some of those techniques?
Well, there's read repair, which fixes things during reads.
Okay.
Then there's gossip protocols, which spread info about changes.
Right, we talked about those.
And Merkle trees, which are like hierarchical data structures that help efficiently compare data between replicas.
Yeah, that's a lot of work just to keep things consistent.
It is, but it's all necessary in a distributed world.
This deep dive has been incredible.
I agree.
We've learned so much about storage engines, distributed systems, consistency models.
It's been quite a journey.
And for our listeners out there,
Yes.
I hope this has given you a much deeper appreciation for the amazing engineering behind databases.
It's a truly fascinating field.
Absolutely. And if you want to go even deeper,
Uh-huh.
check out Database Internals. It's an awesome resource.
It really is.
Well, I think that brings us to the end of our deep dive.
I think so, too.
Thanks for joining us on this adventure into the heart of database systems.
It's been a pleasure.
Until next time, keep exploring, keep learning, and keep diving deep.